Okay, let's take a look at our main ideas for the week and get warmed up for what we're doing. So these are our important ideas up to now. So what we've done is looked at a situation, decided if it's binomial by checking these conditions. If those conditions are satisfied, then we can use the formula. We use the calculator generally, but technically this is the formula that we're using. The thing that kids get confused the most on is this part of the formula. This just means that we are essentially looking at all of the different ways that we can arrange a certain number of successes and a certain number of failures given the probability of those successes and failures. So like our basketball situation where we had different ways we were writing out the makes and misses and finding the probability associated with each of those combinations. Then what we did is we looked at basically how to describe a binomial distribution. And essentially, once you know if something's binomial, you have a formula for calculating the standard deviation and the expected amount or the mean. And those are given here. So sometimes you have to use those once you know it's binomial to figure out where the distribution is centered at and how much it varies by. And then from yesterday, we did from yesterday, day is it? We did two different conditions. And so sometimes situations look a little wonky and we don't know if they're exactly binomial or not, but there's two different conditions we can check where we essentially feel okay, or we can use something else to approximate a probability. So for the 10% condition, we use that when we have a without replacement scenario. And basically we pick something and don't put it back, and that sort of messes up our probability of success. And so we just have to make sure the sample we're pulling is coming from a population that's big enough. Specifically, we want it to be no greater than 10% of the total that we're drawing from. And if that's the case, then we can still use the binomial equation from the previous slide, or the calculator in our case. And then for the other scenario, sometimes we can then also satisfy this condition, which is called large counts. And that essentially just says that, hey, if that works, then we can also use the normal distribution instead. So if you don't want to use this crazy formula in the calculator, as long as this condition is good to go, then you can also just calculate a z-score and get the probability that way. So let's take a look at this question to practice those ideas with. So for this one, it says, suppose that 65% of high school students eat breakfast. So that's a fact that we have. A random sample of 500 high school students were surveyed. Let X equal the number of high school students in the random sample of 500 who eat breakfast before going to school. So for this one, for the first question, it says, explain why X can be modeled by binomial distribution. So what we kind of want to think about is like, okay, well, why is it failing, and which one of these two conditions should we check for to see if we can, satisfy it and then still use the binomial situation. So in this case, I don't want to sample the same high schooler twice. So I'm essentially assuming I'm taking the 500 kids and I'm not putting any of the kids back, because I don't want to ask, the same kid 3 times if he eats breakfast. Like, that would mess up my data. So this is a without replacement scenario in terms of picking students. So what we want to think about is how many students did we pick and where did we pick them from? So in this case, we have 500 high school students and we're picking from high school students. So it doesn't specify that it's from one school or anything. It could be, high school students that ever existed that we chose from, or in the United States or something like that. So it doesn't say it's just from one school. So what we want to think about is, okay, well, is 500 less than or equal to 10% of like all high school students? And so to think about like how big at least this population would have to be, let's just kind of solve for it. So like dividing by 0.1 each time on each side. So 500 just kidding, don't divide. think logically. Yeah, well, okay, just kidding. Yeah, we can divide. That's fine. What day is it? Okay, so if we divide this, that's going to tell us, brain is not working anymore. That's going to tell us that that's going to be 5,500 divided by 0.1 is how many like high schoolers we'd at least have to have. So we have to think about it. Are there more than 5,000 high schoolers ever? Yes. So probably the sample of 500 is less than 10% of all high school students. So we can assume independence. Basically, that condition would be kind of messed up because we're not putting the kids back, but because the sample we're picking is small enough, we're okay with that. So now that we're okay with that, use the binomial distribution to calculate the probability that 300 or fewer high schoolers in the sample eat breakfast before going to school. So what I want to think about is 300 or fewer. Is that greater than, less than, equal to? 300 or fewer means I can be up to 300 students that eat breakfast before going to school. So that's kind of we're looking at 300 or less, so X is less than or equal to 300 for the number of students that eat breakfast. So this is not exactly 300 students that eat breakfast. It's a less than situation, or at most is another way to think about it. So we have binom CDF. And then on the calculator, we always type in the number of trials, or we have 500 students. Then we have probability of success being eating breakfast, so 0.65. And then we've got 300 that we want. So then on my calculator, I just got to type that in. So calculator on. So we've got second, bars, and then go to binom, CDF, hit enter, type in your numbers, 500 times 0.65, comma, however many successes you want to go up to. So 300 at most, at least 300, or at most 300, 300 or fewer. Thank goodness. Okay, and then we get our probability. So that's about 0.011. You can round it wherever you want. I'll throw another 3 on there. Why not? So that's our chance. So we have a 1.13% chance of, out of 500 high schoolers, that 300 or fewer of them would eat breakfast. So not great. So eat your breakfast, kids. Eat your Wheaties. Okay. So then the other thing that we can do is, so that was cool. So we did something with the, the 10% condition, said, hey, it's a-okay to use that binomial formula. That's gonna be close enough. But we can also check that other condition and see if we could just get a z-score for this thing, and if it's close enough that follows the normal pattern as well. So let's check that condition. That's n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So I want to find those two things. So n is 500, p is 0.65. So 500 times 0.65 is 325, which is greater than or equal to 10. So that one's good. So then n times 1 minus p, so 500 times 0.35. It's going to be 175. So that was good. So we can use the normal distribution because the large counts condition has been satisfied here. So our large counts condition is satisfied. We expect 325 successes and 175 failures, both of which are greater than 10. So now I can think about this a little differently. So I can say, okay, well, this situation is close enough to like a bell-shaped curve. So if I was able like to plot out all the different kids, you know, the chances of having all of the different numbers out of 500, how many of those get breakfast, it would follow a bell-shaped curve. So sweet. So we want to know 300 or less, which really, if I want to draw this accurately, it was a 1% chance. So really 300 has got to be like way down here. It's a tiny little space. But now in order to use the normal distribution, my z-score formula, I usually take my data point, whatever that is, in this case 300, minus the mean divided by standard deviation. But they didn't give me that. Shoot. Oh, wait, I have a formula. Okay, so that's our is n times p thing, and the square root of n times p times 1 minus p. So I already found n times p, actually. It's right there. So 325. And then we got to do the other one. So that's our standard deviation. So that's going to be 10.67 if I round. So that's my mean and standard deviation that I want to use for my z-score. So if I plug all this in, 300 minus 325 divided by 10.67 is going to be negative 2.34. So then we got to look that up on our little z-score chart. So negative 2.3 over to the 0.04 column. So our area here equals 0.0096. So we essentially have a 9% chance, 9.6% chance when we use the normal distribution to approximate this, of getting somebody, you know, 300 or fewer students that eat breakfast. So that's a little bit lower than what we got using the binomial formula. Again, this is not a perfect binomial situation. We just feel pretty safe, you know, since our conditions are verified, that we can use the normal distribution as well. And in stats, we would just say these two numbers are close enough. So yeah, this is about, you know, almost 1%, and that was 1.13. This is, you know, 0.96%. So close enough. That's about what we would expect. We feel good about each of the estimates because both of our conditions allowed us to use, you know, calculate the probabilities in the way that we did. So we feel okay about that. We feel okay about it.